Okay, so let's skip some of the subsessions and come to this session at page 251. 251. Okay, it's session 8.8. We'll be doing constraint this square, constraint this square. Okay, so at times we are confronted with LS problems whose unknown parameters must be constrained. How come it's constrained? Think about it. Let's say you're measuring a DC level, and you know there will be an upper bound and lower bound in the DC level a priori. 例如说，你这个 DC level 上下限你已经知道，下限搞不好就是1伏特，上限就是10伏特，因为你从硬体那边搞不好你早知道了。哦，所以有时候会有这种状况，就是说你预先知道一些 constraint 关于 parameter 的 constraint。Okay, so this is the constraint version. And then how do we deal with the constraint? If you have taken the class of optimization, I guess this will not be stranger to you, because you think about this is an optimization problem with constraints, right? Objective function being the j theta, constraints being the constraints. Okay, so that will be easy. That will be easy. For example, you have a linear constraint like this. Linear constraint. Theta 1 plus theta 2 equals to 0, or you have this kind of constraint. So you have a linear constraint A theta equal to B, and A is the R by P, B is the R by 1. If, for instance, P equal to 2 and one parameter is known to be negative of the other, then the constraint would be theta 1 plus theta 2 equal to 0. Okay, so we are resorting to the Lagrangian multiplier. So we determine theta c by minimizing the Lagrangian. And you know Lagrangian there will be a multiplier lambda t. Okay, 对于这个 Lagrange 的方法不太熟的，可能需要稍微 review 一下以前在算那个 optimization 问题的时候，其实在多项式的 optimization 也是有用到的，只是这里其实也是多项式，只是说这里的变数都是 matrix 啊，其实是大同小异的。Lambda is the Lagrange multiplier, and then you expand that expression, you get this, and you partial j, partial c. You know what we are doing here? 是不是大家都了解我们在做什么呢？这里，这个就是 Lagrange multiplier 的标准做法。你先放一个 Lagrange multiplier 之后，你对它做微分，然后令它等于0，然后再解 Lagrange multiplier 跟解 unknown variable 这样。哦，这个是标准做法。So I'm not spending too much time on this. Okay, so you do the JC partial theta and set it to 0, you get something like that, where theta head is unconstrained LSE. Lambda is yet to be defined. To find lambda, we impose a constraint so that this is equal to that, and hence this is equal to that. And then you get lambda, right? You get lambda. You're happy because you can put it here. And then substitute into it, you get a solution. So you get a theta equal to that, where this theta head equal to this. The constraint LSE is the corrected version of the unconstrained LSE. And if it happens to be the constraint is fortuitously satisfied by theta or this, then the estimator are identical. Such is usually not the case. Okay. So what that means is the constraint can be equal to unconstrained if there is a coincidence, but it's not usually the case. So the constraint signal, as an example here, the signal model is like this, and we observe this Then the observation matrix is like that, like that. Okay? Let's not look at the space because the space is a vector. It's a perspective to understand it. But in terms of calculation, it's fine. We just write it out, and theta has given. You get s. You get s. Okay. Now assume we know a priori. This is what I assume. I mentioned many times. A priori means you know before observation. 你事先知道而不需要量测就知道的东西叫做 a priori. So that theta 1 is equal to theta 2. In terms of this, you get this as a constraint, okay? As a constraint. So you have theta t and theta t, and eventually you get SC, okay? So we'll be done with the estimator, And I think I'd like to thank you for taking this class and learning this. I think that's the end of the lecture of this class, and later on we are going to have other practices by TAs, but I think for this chapter we'll stop right here.